Hello, my name is Mark Gibson, and you're listening to the podcast version of the Teagasc Signpost Series, a weekly webinar that promotes and examines sustainability in Irish farming. A very good morning, and you're very welcome to today's Signpost webinar. We hope you're keeping safe and well wherever you're joining us from today. Today, we're going to be discussing the Agricultural Catchments Programme, and today's webinar is part of a series of activities that are going to be taking place over the next week, and we'll hear a little bit about those in a few moments. Just to give you a little bit of background on the programme itself, the programme is run by Teagasc and is funded by the Department of Agriculture, Food and the Marine, and has been in operation since 2008 and has amassed a huge amount of data during that period. And the primary objectives of the programme are to analyse the effectiveness of the National Action Programme, more than measures within the nitrates programme, and also to support the changes that are needed within the NAP or National Action Programme to achieve excellent water quality. And today we're going to be discussing the trends in water quality using some of that data, and I'm delighted to be joined by Dr. Per-Erik Mellander, who's catchment scientist with the ACP or Agricultural Catchments Programme, and also Jason Galloway, who's hydrochemist with the Catchments Programme. And finally, we have Eddie Burgess, who's catchments specialist with the Agricultural Catchments Programme. Before we get talking to Per-Erik and Jason, Eddie, you're going to maybe just give us a little outline and we're going to help us with the questions later on, but maybe give us an outline of what the activities are planned for Agricultural Catchments Week, which starts today, effectively.
Yeah, Mark, this is kicking off ACP Week, and from today right up until next Friday, we will have a series of activities. We're here this morning talking about water quality issues. The Agricultural Catchments Programme this time was our remit was expanded to take on gaseous emissions, and next Friday the Signpost webinar will be looking at soils which influence climate change through carbon sequestration, but also on our monitoring with eddy covariance towers and carbon dioxide. And throughout next week, we have a number of podcasts and various media releases on the radio and in the press and on Teagasc Daily. But it's all culminating with an open day in our Timoleague catchment, which we'll hear more of the results later in this webinar. But in Timoleague, at 11 o'clock next Friday, we will have an open day looking at all the research that we undertake and have been undertaken, as you said, for the last 14 years, monitoring water quality and evaluating the regulations. And there is rays of light over the last 4 years of changing in water quality in a positive direction.
Great, thanks, Eddie. So Timoleague, for those of you who aren't aware, is County Cork, I think, isn't it, Eddie?
Very near Clonakilty.
Near Clonakilty. Okay, so it's a good bit down, but great opportunity to meet the team and see some of the results. And I imagine the farmers will be on hand as well, and to meet with anybody who wishes to go along. So great opportunity to get a under the bonnet look at the Catchments Programme. Full details of that, I presume, are up on the Teagasc website, Eddie.
They are, yes.
To get the directions and air code and all that. So, Per-Erik, you have quite a varied job. I know you're from the lab right out to the field with your work. Maybe could you tell us a little bit about the work that you do with the Catchments Programme, so people have an understanding of the nature of what you do?
Yeah. Thanks, Mark. So I'm managing the water quality research within the program, and having a kind of overview of the whole continuum of following nutrients, mainly from the source by different pathways, and how it might end up in water. And doing research, and as you said, all from the field up to doing analysis and trying to understand what is actually happening. And the more we can understand of this, of course, the more we can do to prevent these nutrients from ending up in water.
Yeah. So you have a really unique expertise on the pathways and particularly within the Irish landscape and geology. So I say that so people can have an idea of maybe the types of questions that they can put to you at a later stage. And Jason, you're the hydrochemist on the program. Could you tell us a bit about the nature of your work?
Sure. I do everything to do with water and how it transports nutrients from fields into streams or groundwater. So I'm kind of looking at physical characteristics of the media that the water is passing through and so on, and how those influence what we're seeing in our test catchments.
Okay, great. So, okay, brilliant. So Per-Erik, we'll hand over to you and look forward to your presentation.
Okay, well, thank you very much, and good morning, everyone. I'm Per-Erik Mellander, and I'm going to talk, give kind of a little of an overview of the water quality status and trends in the agricultural catchments, and also maybe explain a little bit what might lie behind what we're seeing. So first, I'll start off. The Catchments Programme started in 2008 and is ongoing, and is funded by the Department of Agriculture, Food and Marine. And it's collaboration with just over 300 farmers across 6 catchments in Ireland. And the approach is to combine biophysical and socioeconomical research with knowledge transfer. And we're a very big team of scientists, advisors, technologists, and technicians. And the aim, well, the purpose is to monitor the effectiveness of the current good agricultural practice measures and provide science-based findings for policy review, but also to monitor the influence of irrigation farming. So we do this in 6, roughly 10 square kilometer agricultural catchments, chosen to represent the variety of landscape typologies in Ireland, but all chosen to be on intensively managed agricultural land. And the sizes of these, the 10 square kilometers, is chosen to be large enough to include the variability of the landscapes and everything in this catchment that I will talk a bit more about later, but yet small enough to be able to detect changes and not being influenced by too long time lags. And we use, a strength of it is that we use the same experimental design in all 6 catchments. So, excuse me, in the outlets, we have high temporal resolution monitoring of both hydrology and water quality parameters. So as you see here in the river outlet in one of the catchments, we monitor nutrient concentration, nitrate N concentration, total phosphorus, total reactive phosphorus, and a few other parameters, concentrations, and also water flow every 10 minutes. And this has been done since 2009. So there's a lot of data between each parameter. It's more than, well, up to about 500,000 parameters on each parameter. And the reasons for having that is that it captures all. We don't risk skewing the data by a few sample points. And also it captures low and high flow conditions. And we can, by capturing all, we can detect subtle changes in water quality. And that's needed when, for example, understanding the influence of the kind of slow changes induced by weather shifts. But it also provides a process-based understanding. And with this type of data, we have been able to develop methods that we can separate pathways, how nutrients move in the landscape, and also methods that we can identify and quantify point sources and even diffuse pollution. And I will show you methods later on that we use. So what we monitor in the river outlet is a mirror of the landscape. And the Irish landscape is quite complex and contains different soil types, geology, land use, topography, and loads of things. And all things that affect how nutrients, which pathway it takes in the landscape, and then also the associated transfer times and processes along those pathways. So the 6 catchments represent these different types of settings and scenarios. And nitrate, phosphorus, and sediment loss varies highly between the different settings. So if you think this, you see in this figure the complexity that could be in the landscape. If you imagine that as a catchment and you add agriculture sources to that and weather as drivers of nutrients, then what we monitor in the outlet will reflect all that and be a mix of both agriculture sources and weather and be controlled by the different land units. So it's quite filtered signal and mix of both. And it doesn't necessarily, what we monitor in the outlet is not necessarily reflecting the sources because it's so filtered and there's so much influence of other factors. In some cases it will, in some cases not. And if you imagine then the size of this catchment, that will include more of this landscape and dampen the signal a bit more. And it will also introduce longer time lags. So it mightn't be representing agriculture today. It might be a mix of what we're doing today and what we did for about 10 years ago. So we need to understand all this when we analyze all the data. These are the 6 catchments that we monitor across Ireland. And in the little boxes below, you can see the average concentrations over 13 years of total reactive phosphorus in milligrams per liter, nitrate N in milligrams per liter, and then the Water Framework Directive's aquatic ecology status. And there are environmental quality standards, and for reactive phosphorus, this is 0.035 milligrams per liter. So, and then for nitrate N, it's 2.61 milligrams per liter. So with this in mind, I've color-coded this in kind of traffic light colors. So red being above these standards, and orange being very near, and green being below. So as you can see here, 2 of our catchments are high in both nitrate and phosphorus. And one is high in phosphorus and one is high in nitrate, and 2 of them are below in both. So it's quite different. And they are this for very different reasons. And that's a little bit what I'm going to go into a bit later here. But I also want you to notice that there's actually rather poor correlation between the Water Framework Directive's aquatic ecology status and the nutrients concentrations. This is quite complex relation and something that we certainly need to look into more. Here is the nitrate N concentration and the interannual trends in all the catchments over from 2010 to 2022. And to the left is tabulated, so a number per year. And then the color codes is the 4-year rolling Mann-Kendall trend. So the gray is that there's no trend. Blue is stable, that is a stable trend, no change. Red increasing and green decreasing. And to the right, you see actually the very same data, but graphed in the annual average nitrate concentrations, the dots, and the line is the 4-year moving average nitrate concentration. So literally what you can see here, that there are some changes in trends across here. These are short period trends in 4-year periods. So mostly we have high concentrations during these 2 years, 18 and 19, and also increasing trends during this period. And this is very much due to a kind of an outlier year in 2018, when we had a severe drought building up high nitrogen pools in the soils. And then there was a big flush out of these in the autumn. And this really elevated nitrate concentrations in all our rivers in monitored in the ACP. And all the kind of periods looking at trends that ended with these years had an increasing trend. And it really offset the whole picture. And if you then look at now, more recently, we are actually seeing a decreasing trend. And actually in Timoleague, as Eddie mentioned before, the concentrations at 2022 is lower than it has been during our period of monitoring. So I won't go in too much now in what is the underlying cause of these trends in nitrates, because I know Jason will be talking shortly on more in detail on nitrate trends and concentrations in subcatchments. So instead, I will actually now move on to looking into factors controlling phosphorus. Some of them, of course, will be very important also for nitrate, but a very important factor is the soil drainage. So what you have here is a graph on total phosphorus loss in the load, in kilos of phosphorus per hectare and month, and the stream flow in millimeters per month for two catchments, one well-drained catchment and one poorly drained catchment. So the well-drained is blue and the poorly drained is red. And these are just very short distance from each other. It's two Wexford catchments, but you can clearly see that for the same river flow, you have 2.5 times more loss in the poorly drained catchment. And there's no big difference in the amount of sources here. So this is an example of where actually the hydrology can override source pressure, because this catchment with poorly drained soil has a very flashy hydrology and kind of erosive hydrology, and a lot more phosphorus will be carried out in the runoff in this catchment. And you can also see a larger seasonality in this catchment because it responds quicker to shifts in weather. Another factor that's very important is the soil chemistry. And this is a similar type of a paired catchment approach where we look at two mainly groundwater fed catchments. One is aluminium rich, is the Castle Lockrow catchment in Wexford, and one is iron rich soils. That's the Timoleague catchment in Cork. And you see that here is the water soluble phosphorus and Morgan's P phosphorus, and both phosphorus forms complex with both aluminium and iron, but with iron it tends to be more soluble and will easier be leached to surface to groundwater, to shallow groundwater, where it will end up in the river. So other factors, both aluminium and iron, but also calcium, is a controlling factor for both P retention and solubility. And this will influence the phosphorus loss even at the catchment scale. And we see that this iron-rich catchment actually has twice as much phosphorus leaving by below-ground pathways than the aluminium-rich. The proportions are the same, but it's just higher concentrations. Other factors are critical source areas. It's very, very good to know about where these are. There are some areas where phosphorus sources on the surface are directly connected, hydrologically connected to the rivers. And these will contribute a lot more than to the overall phosphorus loss. But they're not only critical areas, it's actually also critical times. So there's some times that are more sensitive to loss. And when looking at doing interannual comparisons and looking at trends of that, you might be missing things then, because sometimes it could be the loss could be just a short season when things are happening. So trends could be in the seasonality rather in the different years. And then also another complexity of looking at trends is that there are critical pathways. And when you monitor in the river, you mightn't observe a trend, or you might see a trend, but actually that might be driven by only changes in one pathway or two pathways. It could even be counteracting pathways that makes that you don't detect the trend. So it's very important to be able to separate the pathways, which is also a strength for being able to say where the losses are, but you can also then see where the changes are. And then to know, to be able to identify point sources versus diffuse losses. So these are all ways that facilitates the knowledge for better management and advice. Then we also need to know about weather and the influence that weather has as a driver of nutrient loss. We have the sources, but they wouldn't be lost if there wasn't a mechanism driving this loss. And there are both long-term shifts and short-term extremes. And the first here is an example of the long-term shift. You see nitrate N concentration on the y-axis. That's annual averages in one catchment. So each dot is a year of 10-minute data composed into one dot. And then you have on the x-axis something that's called North Atlantic Oscillation Index. So that's just one number that illustrates a big weather system over the Atlantic and how that intensifies some years. So if you actually plot these against each other, you see there's a fairly good correlation. And this is quite strong in some catchments and less so in other catchments, and sometimes for nitrate and sometimes for phosphorus. So in this case, this illustrates this kind of long-term changes that might be difficult to detect by looking at short-term monitoring. But then there are also the weather extremes, and this is an example. You see the photo here to the left is surface runoff on actually well-drained soils. But this is in November when the soils were saturated and received excessive rainfall on top of that, and generated huge surface runoff. So if you look in the graph on the right side, you see a big spike, and that's the same period. That's 13th and 14th November 2014. And over those 2 days, this catchment lost more than it does normally over a full year. So it's 106% of annual average loss only over these 2 days. And then you can have drought-induced nitrate loss as another type of weather extreme. I already mentioned that during this big drought we had in 2018, when you build up the nitrate pool and by poor growth, but also by mineralization and other factors. And then in autumn, when rain comes, this pool is flushed out. And we saw that in all the catchments, and more so in the grass catchments. And an example here in the graph is nitrate N loss in kilos per hectare a month and river flow. And you can see the red dot there, that's in November 2018, just after the drought with the first rains flushed this out. And this month was 54% of the annual average loss on nitrate. So with this high frequency data, the very frequent monitoring of nutrients, we have been able to develop new methods, as I mentioned before, and separating pathways, but also to quantify and identify and quantify the amount of diffuse pollution, which has always been tricky. And this allows us to do a systematically objective way of describing diffuse pollution. And how we do that is we create what we call a mobilization index. And this is in the same way as hydrologists will do this to create to be able to say something about the flashiness of a catchment. And even economists do the same with salaries, and they look at percentiles, ratios of percentiles of salaries to be able to talk about inequality. And we do the same here, having such a wealth of data on concentrations. We can look at the top 5% of the concentration divided by the the lower 5%, so the 95th percentile divided by the 5th percentile. And this will integrate processes that contribute to the concentrations in the catchments, in the river outlets, such as soil phosphorus detachments and solubilization. And we can do the same then also with the mass loads, the weight of the phosphorus, and get an indication of the delivery of phosphorus, such as hydrological connections or phosphorus retention. And the reason we want to do this is that they characterize the catchment's phosphorus transfer, but also we can analyze the stability or even look at trends in this. And also, it allows us to analyze transfer processes for model scenarios, so we can look into the future, what might be happening. And I'll just quickly give you an example of that before I wrap up. These are the mobilization indices in all the catchments for total phosphorus at top and reactive phosphorus at the bottom. And they're ranked from the highest mobilizations to the lowest. And this matches our conceptual understanding of these catchments very well, with a higher mobilization in the groundwater-fed catchments and lower in the surface-driven. And then this is the same for the delivery index, with a higher in the flashier catchments and lower in the more groundwater-fed catchments. And then we can also look at the trends in these, and literally you can see that some catchments have been quite stable, and some have gone up and some have gone down. And this allows us to really understand what might be happening in these catchments. And I'll give you now an example of how this practically can be used. Using what we call the phosphorus transfer continuum, where we follow the phosphorus at all stages from the sources via this transfer to delivery and impact. We have an idea already of the sources, and we have that in stocking rates. But so this is in kilos organic phosphorus per hectare in all the catchments. What's supplied there, and these are color coded. Again, red for being excessive and green for being low. Some of them have little. Some of them are Balcanu and Dunleer here are red despite being low numbers. And they have little pluses there, and that's because we know that there's also slurry going into these that wasn't included in this number. Then we have mobilization index that we calculated, and again, some are high and some are lower. It's the traffic light color code again, and then the delivery. So this is also calculated from this index. And then we have the impact. That's what we monitor in the outlet. So now this is where it gets interesting, because now we can see what might be the risk. So if we take, for example, these two catchments, Cordoff and Craigdoff, they both have low, well, they actually both have high sources, both red there, and then the impact is low yet. And now we can understand why, because neither of them have high mobilization and delivery risk. So it doesn't matter if the sources are that high in these catchments. But we still have to be aware that processes might change in the catchment. That's why the trends are important, and to understand the catchments. So if any of these mobilization and delivery processes will increase there, then we're in trouble. Then the impact might increase there. And Casodocrel is kind of the opposite. It has low sources, but it has high mobilization. But since it hasn't had much sources, it doesn't matter that much phosphorus is mobilized, so the impact becomes low. But then it's potential mobilization risky, because if the sources will increase there, we know there's already high mobilization in that catchment. And then finally, we have the three catchments where impact is high, and we can see why there's high sources, but there are different reasons for the transfer there. In Balcanu, it's about the delivery, and in Dunleer and Timoleague, it's more about mobilization. So this is a kind of risk screening tools that can facilitate some planning here in mitigation strategies. So I'd just like to summarize this now, that the Catchments Programme is building a robust scientific understanding on the factors affecting nutrient loss. And these are, as I mentioned, critical areas, critical times, and critical pathways. And source pressures alone does not entirely explain stream nutrient concentrations. There are other factors that can influence there. Physical and chemical factors and weather influence nutrient loss. And then measures need time to be adopted and implemented on farms to deliver a positive impact on water quality. And then finally, we have this new P-index method that can be used as a risk screening tool. So with that, I'd like to thank you very much, and I'm open for some questions.
Thank you, Per-Erik, and thank you for stepping us through some of those complex enough slides there. Very at a nice pace there, because yeah, it's good to really understand that, and I really like that transfer risk screening tool. So maybe we can talk about that after Jason's presentation, because I'd imagine there's quite a few questions around that, and really looking at how that can be put into practice. So Jason, if you're there and you can share your screen with us, if we could try and keep it to maybe 10 minutes so that we can have good time for questions and answers. We already have 7 questions coming in from our audience. So we'll maybe ask you to keep it relatively moving at a reasonable pace, we'll say.
Certainly, yeah. I'll give you all a vignette on. So Per-Erik mentioned about the data set that we've collected, which is it's fantastic. The volume of data. He spoke a lot about the high frequency data that we collect at the outlets. So that's at the drainage point of our catchments. I'm going to speak a little bit about how we've been using that data, but how we've also been using data that we collect on a monthly basis nested within our catchments. And I'm going to show you how that's allowed us to further our understanding on the controls and the drivers for the movement of nitrate into stream water. Okay, so I won't belabor the point on why we need to reduce nitrate concentrations. I would imagine that most of you in the audience know that a lot of waters in the south and southeast of Ireland are failing to meet the Water Framework Directive's standard for water quality due to the concentration of nitrate in surface water. And as Per-Erik mentioned in his presentation, the processes that take us from a load on a field to a measured concentration in stream water, they're complex, and they vary in time, and they also vary in space. So that presents a challenge when designing experiments to further our understanding. There's a compromise that needs to be made between collecting a lot of information in one place or very few places, or collecting little bits of information in many places. And so the benefits that you have of collecting a lot of information is you can capture weather events. So for instance, there could be an extreme flushing event where a significant portion of the annual budget for pollutant leaves. And if you're only doing 6 monthly sampling or annual sampling, you can miss these events. On the other hand, if you only focus on one location and you have a lot of data, you miss some of these, you may miss some of these critical areas in the landscape. What we've done is we've tried to combine the best of both worlds, and we've adopted what we call the sub-catchment approach. So we used 4 of our 6 catchments in the ACP, and what we did is we broke down each of these catchments into smaller units, which we call sub-catchments. And the way that we define the boundary for these sub-catchments is by water drainage. So each of these yellow circles along this blue river channel, that's a sampling point where each month we took a water sample and then analyzed that for NP and a whole host of other compounds. I'm only going to focus on nitrate in this talk. And so these subcatchments, they go all the way down the stream river. They're nested within one another, meaning that subcatchment 5 contains 6 as well as 5, and 4 contains 5 and 6, and so on and so forth, with the exception of tributaries. So if there's a tributary then that's not necessarily nested in within these other subcatchments on the main channel, but they will all be nested within the entire catchment, which we also considered in our analysis. Okay, so in each of these subcatchment units, we collected data to represent processes that we know are key drivers or controls on the movement and the cycling of nitrogen to nitrate, and then its subsequent transport to surface water. So we collected information on land use. So was what was the proportion of land in arable versus land in grassland. We collected information on farming intensity. So for livestock, their stocking rate, and for arable, we assumed mineral fertilizer application of 130 kilograms per hectare. We also collected information on the prevailing soil drainage characteristics in each of those subcatchments. And finally, we also combined that with the North Atlantic Oscillation Index, which is a climate indicator, which Per-Erik mentioned in his presentation. Basically, what that indicator tells you is how extreme is our weather conditions in a particular area for that period of time. So it's giving you an indication of extreme dry weather or extreme wet weather, just anything that is atypical. Okay, so once we had compiled this data set, we used some statistical analysis to kind of bring everything together and analyze it, so that we could glean some understanding as to which drivers and controls are more important, and also how, when, where, and why. So I'm going to take a little step backwards. And so these two figures, they're at the top here is the farming intensity. That's the source loading or the stocking rate in the Dunleer catchment. And at the bottom is still the Dunleer catchment. That's the stream water nitrate concentrations. And I just want to bring your attention to one of these subcatchments. So each of these lines represents a different subcatchment. And this red line, these markers from 2010 to 2018, that was one of the least intensively farmed subcatchments. However, it had consistently the highest stream water nitrate concentration. So this isn't always the case, but this is the type of thing that you can see when you break down a catchment to smaller units. And the good thing and the useful thing about doing that is you can compare like for like. So if you were comparing one catchment to a different catchment and you saw something like this, you might wonder, is there something different that I didn't record in for instance, local practices, local farming practices that's influencing why we're seeing this. But if you're looking within the same catchment, you can be more confident that many things are similar. Okay, so to stay with Dunleer, so to dig a little deeper and understand, so there's quite a widespread in source loadings in the different subcatchments, and also quite a widespread in the stream water nitrate concentrations. And one of the key reasons for this is, so using our statistical analysis, we examined the impact of the percentage of freely draining soils within a subcatchment, and asked the question using this method: if you change the percentage of freely draining soil, how would you expect your stream water nitrate concentration to change? That's what this figure over here is showing at the bottom right. So as you go from 0 to 100% freely draining soil within a subcatchment, you can expect that there's an increasing trend of, this figure shows how does a subcatchment change in relation to the average value. That's why it's centered around 0. So you can see as you get above 25% or so freely draining soil, you have quite a steep increase in expected stream water nitrate concentrations. The other thing that's important to note is there's also a wide error bar here, and that's due to the other factors which mediate the transport processes. So soil drainage is important, but it's not the only characteristics that will determine how much nitrate you can expect to lose from a subcatchment here. Okay, so to sum up, what were the key findings? So I didn't go into everything here. We had around 36 subcatchments, and we did analysis looking within catchments and between catchments, and then all of our data together. And the overall findings were that climate and soil drainage were the most key controls and drivers of stream water nitrate. Source loading didn't have a statistically significant relationship with predicting stream water nitrate concentrations in any of our catchments. The reason for this is that all of our catchments are intensively agricultural, and the chemistry of nitrate is such that it's very mobile. It dissolves in water. Its formation is dependent on climate and soil factors like the amount of organic carbon that's present in the soil, how aerated it is. So these factors, they override source pressures. So I've gone a little bit over time there, so I'll wrap up. And if there's any questions, please do ask.
Thank you very much, Jason, and thanks for sticking to time there, because I do want to leave some time for all the questions, because we are getting a lot of questions here, a lot of interest in both presentations this morning. So do use the Q&A tab at the bottom of your screen if you'd like to put questions through to our speakers. So I propose Eddie, we'll probably go straight into the questions, because we want to try and answer as many of those as possible. But thanks both to Per-Erik and Jason for keeping your presentations accessible for us all.
Yes, Mark, we'll get straight to it. I suppose a very straightforward question came in first. What equipment is being used to continuously monitor nitrogen and phosphorus every 10 minutes? And how good do we find it? Is it consistent and is it reliable?
Yeah, should I take that one?
Yes, Per-Erik, sorry, yeah.
Oh yeah, thanks. Yeah, so no, that's a very good question. It's a lot of time spent on exactly this, a lot of time and effort. So for nitrate, it's an optical sensor that's put in a tank that we pump up water into continuously, and it continuously monitors nitrate N with this, and this is calibrated frequently and cleaned and so on. So we have on-site technicians that work with this on a full-time basis across all the catchments. So this is calibrated frequently, as I said, and samples are taken and compared ongoing. So we can trust this very well. Otherwise, there could be drifts in these, of course, if you just leave them. But we handle that by this strategy. For phosphorus, it's a different method. It's still using the same sites and so on as the optical sensors, but it's actually an on-site little mini lab. It sucks up a sample and with wet chemistry analyzes for reactive phosphorus and total phosphorus by digestion. And this is done also frequently. It's roughly every 10 minutes. It's about every 12 minutes. And again, this is maintained by our technicians being on site and looking after this instrument ongoing. And samples are taken and compared, and we are very confident that this is producing good data.
And Per-Erik, thanks for that. Let's take that. I'm going to focus on a few nitrate and nitrogen questions, which mostly, but not always, seem to be targeted on the Timoleague catchment. Just the improvement that you've seen since 2019 to 2022 year on year. Question is, has that been seen in the other catchments?
With nitrate, there has been a slight improvement, not as much as in Timoleague. Have in mind that Timoleague was one of the catchments where the concentrations elevated quite a lot in 2018 and 19 in the droughts, and thereafter it dropped quite rapidly. And as both myself and Jason have talked about, the catchment responds very differently. So I think we need longer time to evaluate that and why is the cause of the drop and why it doesn't drop as much in all the catchments, and it's a bit different in different catchments. But also I know that the advice has been it has been really afterwards. After 2018 we learned a lot from that, and the advice had been considering this situation. So I think that has improved, but then also the fact
Per-Erik,
that we have
could I pick up on that slide that you presented with the transfer risk screening tool? You showed a different, I think it was organic P concentrations. How does that relate to the index system? If you were to run the indices alongside, what sort of relationship is there? Which index system with
a
phosphorus index?
In the soils, or
Yes.
or you mean in this transfer index?
This transfer tool you talked about, I think was the one on top was 20 kilograms per hectare.
Yes.
What was that? How does that? If we were to look at developing that further, that risk tool. And combining your concentrations with your pathways and your receptor, how would you see that relating to the index system that's in place?
Okay, well, first of all, it's kind of early days. We're developing this, and it's looking very promising, but it's developed from this high frequency monitoring in the outlet, which of course is quite unique, and we don't expect all catchments to have this type of equipment. But there's a very good correlation between this and the hydrology in the catchments. So we can, by understanding base flow in the catchment, we can understand mobilization, and by understanding the flashiness in the catchment, the peaks and so on, we can understand the delivery. So we can use basic hydrological measurements in catchments to understand this, and then we can link it to whatever we know about the sources in the soils. That is where we're kind of aiming this in the future, so we can be able to use this more frequent, and we can use it in modeling when we model future scenarios, so both agriculture and weather, climate change. We can see what processes might be changing in the future and what we need to look out for.
I think the key message is that every landscape, or almost nearly every field, has its own characteristics, and the management has to reflect that.
Yes.
Yeah. Okay, Eddie, sorry for disturbing you on the questions now. I'm conscious we have 8 minutes left, so maybe just for Per-Erik and Jason to keep the responses as concise if you can.
Yeah, I suppose I'm going to go back to nitrogen and then kind of combining two questions that came in together, try and get through. And one of them was a continuation of the previous question on the nitrates in Timoleague, and they're coming around to the fact that the derogation decision has a review taking place this year, and if water quality doesn't reach the required standards in the time period that was specified, that the limit of 250 will be reduced to 220. And that's been reported in the journal. The question is, does the improvement in water quality in Timoleague mean that this is unlikely to happen? And I'm going to combine that with another question, saying that in the overview of the catchments, you show that 3 or possibly 4 of the catchments don't reach the Water Framework Directive quality standards. And after 14 years, does this mean that the good agricultural practice measures are not working? I'm going to attempt a bit of an answer to that myself.
Please.
While the water quality has improved in Timoleague, the objective is that water leaving the river as it flows into the estuary would be below a figure of 2.6. Now in Timoleague, the concentration, I'm talking about concentration leaving, not the load of annual amount of nitrogen leaving, but the concentration on average would be below 2.6. And in 2022, it was at the lowest level that we ever found, which would give hope that the regulations are working. But the lowest level that we found in Timoleague was still almost twice that 2.6 figure at 4.9. And I suppose this is coming back, we're saying it's difficult. You went through the complexities there. There was a comment saying there must be an easier way to explain this. There's huge complexities in water quality, and time is needed to see actions working, but it's a combination of climate, weather, soil, and farming practice. I don't know, Per-Erik or Jason, have you anything to add to my comments there?
I would just add that when considering nitrate concentrations, it's important to take into account what the weather was doing that year. So as Per-Erik had in his slide showing the impact of the drought in 2018, if for instance, you took 2018 as a baseline, every subsequent year would seem to be improving. And likewise, if you took a baseline a few years before 2018, it would look like things are moving in the wrong direction. So I think it's important to have the context around a measurement to be able to understand whether mitigation measures are being effective or not.
Yeah, and a very simple question and just answer no is any survey from forestry planted on the areas and its impact on water quality. The catchment areas were selected to evaluate the mainstream agricultural enterprises, and forestry is not, for areas with significant amounts of forestry were avoided. So that's one thing that we don't have any detail on. And in addition to that, none of the catchments have PC soil types. So we're on mainstream agricultural enterprises on mineral soil types, and they're quite small, as Per-Erik said, around 1,000 hectares. Mark, have you any to follow in there while I read a few more?
Yeah, I suppose just a question there. You mentioned about this relationship between the aquatic status or the water quality status that's measured under the Water Framework Directive versus the chemical status, and that the relationship there is complex enough, and that they're not always correlated. Am I right in interpreting that way? Yeah,
I think that's a good interpretation of that. All right.
Yeah. So what does that tell us then about? I mean, we need to. How important is the chemical status then? If really what the measure is the broader aquatic status?
Yeah, well, I think we have to realize that there are multiple stressors on the ecology, and if when looking at one alone or over just an average, it doesn't really correlate that well in that case, because it's kind of the long-term stress and then the temporary knockouts, so to say, when things happen very drastically. So it's a combined effects of acute and chronic situations, and the combined effects of different stressors. And there have been studies indicating that sediment is probably what sediment and hydromorphology itself is what's influencing most in our catchments. But of course, nitrogen and phosphorus also plays a role in it. But then again, it's a combination of all these, and that's why it's difficult to see a clear link. And then we shouldn't forget that there are other stressors. There's pesticides and pharmaceuticals and all sorts of things, and we all need to combine all of this.
Yeah, you mentioned pharmaceuticals. That's an area that I think there's a lot more investigation to be done there, and maybe an area that we could discuss on one of our webinars in the future. Eddie, we've time for the last couple of questions there. If you want to,
there's a couple of comparisons being made by our analysis and that's undertaken by the EPA and the frequency of monitoring undertaken by the EPA in their Water Quality of Ireland report. I was wondering, do the Agricultural Catchments Programme, do our 6 catchments feed into the national reporting? And I suppose no is the answer to that. We don't. We work very closely with the farmers in the catchments and we have a good relationship with them, and we're carrying out research at their goodwill. And it was decided at the outset that we wouldn't feed into the national report, but we do compare our figures, and we have a modeler working with our programme, and we combine our high resolution monitoring with the figures of the national data set. And we do fit in, our results do fit in with the spread of results that the EPA are showing there. You can kind of see where our catchments would fit in the spread of the results that they're coming. Ours are smaller than the EPA's, and a lot of people might say that our results contrast with the EPA, but they don't. We do fit in, but we don't have. The EPA report on almost 5,000 water bodies nationally between groundwater, rivers, lakes, estuaries, and the sea. So in the rivers, I think there's around 3,000 river water bodies included in that report, and our results would fit in with those.
Okay, thank you, Eddie. We're just up on 10:30, so just want to say a big thank you to Per-Erik and Jason for your presentations. Clear there's a huge amount of work going on in the Catchments Programme, and just the vastness of the data that's been collected is really hard to get your head around. So it's wonderful to have this data set, and obviously this whole area is a complex area, but I think you've drawn out some very nice conclusions there, and obviously there's good work going there and actually into trying to produce practical guidance there for farmers and landowners and how best to manage land. I think the work that's been done on the PIP maps, these risk maps, has been really important work to be able to identify riskier areas. So it's really about building on that work over time. So thank you so much for your presentations, and the presentations, as I said earlier on, will be uploaded to the Teagasc website. And we're going to continue next Friday with our look at the Agricultural Catchments Programme. We'll be joined by Dr. Bridget Lynch and Onion Zurovec from the ACP programme, and they're going to be talking about the gaseous emissions and soil science aspects of the Catchments Programme. So until next Friday, do keep an eye out for all the different activities that are taking place as part of Agricultural Catchments Week next week. I've sent a link through the chat there. And I want to say a special thanks to Yvonne Maher and Andy Boland and Pat Murphy for their work in the background in developing and continuing the excellent series of speakers that we have from a week-to-week basis. So until next week, we will talk to you then, and have a good weekend. You've been listening to the podcast version of the Teagasc Signpost Series, the weekly webinar that promotes and examines sustainability in Irish farming. Don't forget to join us live every Friday morning for our latest webinar. For more, visit teagasc.ie. And you can also rate, review, and subscribe to the Signpost Series on Apple Podcasts, Spotify, or wherever you get your podcasts from. I'm Mark Gibson, and thanks for listening.